In this video, we'll develop a model for a spring mass system that includes no friction, but does include a sinusoidal input force. What you might imagine is a mass, this rectangular block attached to a spring, and then we're hooking a wheel up to it that's rotating around and providing an input force to the system. We're going to model this with a second order differential equation, and then discuss how the solutions to the differential equation might look. Notice that we should have a second order term, mass times acceleration, from Newton's second law. We will not have a first order term because there is no friction. And then we have a term from the spring constant K, which is something related to the springiness of the spring. That's a zero order term. On the right hand side, we put our input function, which in this case is probably some sort of sinusoidal force that's being added into the system. So I'm going to represent that with F naught, that's some constant that represents the amplitude of the signal, and then sine of lambda t, lambda is going to determine the angular frequency of the sinusoidal signal. So the input force is some sort of sinusoidal wave. We're going to have an amplitude of F naught, and then it's going to cycle around, and it will complete its cycle at 2 pi over lambda. Let's divide every term in our differential equation by m, just to make the coefficient of the first term 1, and I'll have k over m, and I'll have some expression on the right hand side. I'm just scaling the right hand side. Ultimately, it's some sine function on the right. As we did before, I'm going to let omega be the square root of k over m. It's just a convenient notation to use to simplify this coefficient. And when I do that, the left-hand side of my differential equation now is going to have omega squared as the coefficient of x. So we now have a non-homogeneous differential equation, and our method to solving those kind of differential equations is to first solve the complementary problem, find the complementary solutions, that is, set it equal to 0 on the right-hand side and find the solutions to this differential equation. In operator notation, that looks like d squared, two derivatives, plus omega squared, applied to my function x, should annihilate it. So d squared plus omega squared should annihilate any solution to the complementary problem. You've done this before in the previous video, but the auxiliary equation will have roots plus or minus I times this omega. So it was convenient to relabel the omega only to make it these roots of the auxiliary equation look nice. So plus or minus I times omega. As such, they're imaginary, and we get sinusoidal solutions to the complementary problem. The complementary solutions, xc, look like c1 times cosine of omega t plus c2 sine of omega t. So this number omega is determining the angular frequency of the complementary solutions. The next thing we do is we look for the particular solutions. We're not going to do this in a lot of detail. We're just going to find the form of the particular solution, see what kind of functions would look like a particular solution. And to do that, we first annihilate our input function. In this case, my input function, this right-hand side, is some constant times sine of lambda t. To annihilate that, I need to use d squared plus lambda squared. Keep in mind, it's similar to this situation. Cosine and omega t and sine omega t are annihilated by this operator, so sine of lambda t will be annihilated by d squared plus lambda squared. We apply that to both sides of our differential equation, our non-homogeneous one. And when we do that, we'll get d squared plus lambda squared times d squared plus omega squared of our solution function x should be annihilated by it, so it should be equal to 0. The roots of the corresponding auxiliary equation will be plus or minus I times omega, and now we get two extra roots, plus or minus I times lambda. You have to ask yourself how many roots are here, and that is a delicate question. If omega and lambda are the same number, you actually have a repeated root occurring in each case. So there's only two roots, but each one is repeated. If omega and lambda are two different numbers, then you have four distinct roots, and that dramatically affects how we write down the form of the particular solution. So let's handle the case where lambda and omega are very different values, or just different values. If they're distinct, then the solutions to this higher order equation I've written here, the fourth order equation, will have our two complementary terms, C1 cosine of omega t plus C2 sine of omega t, and then we'll have two other terms, which I've written here with cosine lambda t, sine lambda t, that are coming from the other root of lambda, I times lambda. Those will be some coefficients in front, and there will be specific values of a and b that will give us a particular solution to the differential equation. So the first two terms are complementary, we would ignore those, and then the second two terms would tell us the form of the particular solution. So xp, the particular solution, is of the form a times cosine lambda t plus b times sine lambda t. You could go through the whole process of finding what those undetermined coefficients a and b are, but we'll put that aside. It's enough for us to observe that the particular solution would be some sinusoidal function. The other case is when lambda and omega are equal to each other. Then we have repeated roots. If I write down the solutions now to this differential equation that's appearing here, the fourth order differential equation, I will see the complementary terms again, the cosine and sine of omega t. But now, because I see a repeated root, I'm going to see a factor of t in the other two terms with the same angular frequency omega t. So t times cosine and t times sine. The first two terms are complementary, so we would ignore those when looking for a particular solution. And the remaining two terms are these trigonometric expressions, but now with these factors of t. And those are our particular solutions in there. So there is some particular value of a and b that you could determine by doing probably a challenging calculation, but you could determine these coefficients a and b and find that the particular solution would be of this form. These functions behave very differently. As I let t increase here, what's going to happen is I will see something oscillating, but that factor of t in front will drive the amplitude up in a linear fashion. So what's going to happen is we will see sinusoidal waves that are being amplitude by that factor of t that's appearing due to the repeated root. And this is a situation which we call pure resonance. In the physical context, I've got this spring which wants to oscillate at a particular frequency determined by this number omega. That's its natural oscillation frequency. But then on top of that, I'm putting in this extra force that's going to be determined by the value of lambda. That's my angular frequency of the external force that I'm adding to the system. When that force of when that external force determined by lambda is exactly equal to the natural resonance of the spring, they will combine and they will amplify in order to get this system that will go off to infinity, and the steady state would start to behave quite erratically if this was a physical system. So what we're seeing here is what's called resonance, where the input function is resonating with the natural frequency of the system.